start with the next talk on a slightly different topic. Stratos Pateloudis has joined us from Regensburg in Germany to tell us about the D0-brane matrix model in the low temperature regime. Please take it away.
Okay, thank you, David, for the introduction. And I would also like to thank the organizers for giving me the opportunity to talk in this conference in this very beautiful place. So I will be talking about works that have been done here and some work in progress. And I also have, of course, collaborators. Georg is here and some other people, which are listed over there. So the plan of the talk, first of all, is to motivate a little bit this work. And of course, it is a non-perturbative approach to gravity and quantum gravity and holography in general. And the question why I'm interested in low temperatures is because in low temperatures, we have analytically known gravity duals. And then we can essentially test a little bit better the holography. So this is the outline of the talk. In the beginning, I'm going to steal a little bit of glory from Georg and introduce how this model is understood. But I will present it in my own way because I try to think about it intuitively. Then I'm going to describe a phase, which is a confined phase in D0 matrix models, and what does this mean. Furthermore, I'm going to switch to simulations to test the idea of holography in low temperatures. I'm going to ask a very simple question motivated by Maldacena-Milekhin about the role of the gauge constraint. And I'm going to discuss some ongoing work about comparing internal energies of black holes and matrix model. And I hope that this will create a little bit of excitement. So let's see. So the model I'm interested in is given by this Lagrangian with the fields and the derivatives appearing like this. But the 't Hooft coupling, it is a dimensionful 't Hooft coupling. It has mass, it has units of energy cubed, which makes this model not to be a conformal model. And of course, you can arise to this model as a dimensional reduction of from different dimensionalities with different supersymmetries. It first appeared in the literature by the Whithope and Nicolai in '88, which was proposed to regulate the 11-dimensional supermembrane. And 8 years later, Banks, Fissler, Senker, and Susskind, they proposed that this model should be a non-perturbative definition of M theory. It is also dual to a specific geometry, which is known as the black zero brane, which is discussed in this paper here. And today, I'm going to focus in these two parts. So let me naively introduce the gauge gravity duality and in full generality, the way I understand it from string theory. And the idea is that black P branes from certain superstring theories, they are dual to P+1 dimensional UN gauge theories, which contain these DP branes plus strings. But in my case, I'm going to consider when P is 0. So here we have a black zero brane in type 2A, and here I will have the matrix model I saw before. So as I said, the 't Hooft coupling is dimensionful. So I can create an effective dimensionless coupling by dividing with appropriate powers of energy. And the idea that the holography works in this case is that, take for example, the bosonic matrices written in red here. So the diagonal elements will correspond to locations of these zero branes, and non-diagonal elements will correspond to open strings stretching from from one D0 brane to another. This information is concerning one dimension. since I have 9 of these matrices, I construct the information about these D0-branes the way they spread in R9. And here I just recall that the bosonic potential has the reflective behavior of phi to the 4th. And the minimum solution, of course, is when all these D0-branes are sitting at 0. So the question is, what does this correspond to in the gravity side? Well, in the gravity side, when you have a stack of D0-branes, this corresponds to a black 0-brane in type 2A supergravity that has these specific characteristics. So this is the metric. It has a horizon when you want to study thermal physics. It has, then one can do thermodynamic analysis, find the internal energy and entropy. And by fine-tuning the radius of this black 0-brane and the dilaton on the horizon, you can study different aspects of the model. So for example, I can fine-tune these two guys here, which can be expressed in terms of the effective coupling, to focus myself in this type 2A black 0 area. But as I'm going to show, it is possible to go to even lower temperatures or lower energies and then flow from this direction towards the right. So I should expect to enter M theory. Now, to understand a little bit this intuitively, type 2A string theory is usually defined as M theory compactified on a circle S1. And the radius of the circle is related with a dilaton, and which furthermore is related with effective coupling. So when I want to open this circle, I have to go to very low energies, because in this case, it will blow up the circle. And reminding that the energy is defined by a temperature, this corresponds to very low temperatures. So the idea is, by going to even lower and lower temperatures, I expect to flow from this area here towards the M theory region, because the 11-dimensional circle opens up. So if I have a black hole along this circle, it will appear very small from the 11-dimensional point of view. So now I'm going to switch a little bit to simulations, but I'm going to give very minimalistic ingredients, and I will refer to Georg's lectures starting tomorrow. So we can put this matrix model on the lattice, and we can use the technology from lattice QCD. And the idea here is that we have just one dimension, so this makes things a little bit easier. And the parameters that control the system is n, which gives me the size of the matrix, the lattice points, and the temperature, which essentially controls the size of the lattice when I want to study thermal physics. So the way I take the large-n limit in this case is by fixing lambda. And then the large-n limit corresponds to large matrices. One more ingredient that I'm going to need is the confinement deconfinement transition. And as was introduced also earlier in Hiromasa's talk, for example, the Polyakov line, you can write it on the lattice like this, and the restoration or breaking the center symmetry corresponds to a signal of transitioning. And the intuition from ADS 5 crosses 5 is that this transition has very specific correspondence in the gravity side. So as reported by these people here, confinement corresponds to a graviton gas where the energy in the Polyakov loop are 0, while deconfinement corresponds to black holes where the energy is non-zero and the Polyakov loop gets an expectation value. So in simulations, for example, I here present Monte Carlo histories and the Polyakov loop, how it fluctuates. So here I can, in the figure above, I start with a confinement phase, and then it transitions to a stable deconfined phase, and this corresponds to a black hole. On the other hand, in the bottom figure, I have the inverse situation, where I start with the deconfined phase, and then I transition to confinement. But the gravity theory predicts that there shouldn't be any confinement. And this is given because the energy cannot be zero for non-zero temperature. But this simulation here are at non-zero temperature. One more caveat is that these simulations are finite n and finite lattice sites. So I have to make sure that this confinement phase survives in the large n and continuum limit. So I saw this exactly in this slide. And I want to bring to your attention, for example, the left panel. I do large n and specific lattices at 0.2 temperature. And you see when I do the large n extrapolation, the Polyakov loop, which is the green line, goes to 0. On the other hand, for the same parameters, the same temperature, I do continuum extrapolation by keeping n fixed. In this case, it is the energy, which is this red line, that goes to 0. So when I combine both, I have to conclude if I have confinement or deconfinement. Now, deconfinement phase predicts finite values of energy and Polyakov loop. So if I conclude, so what I conclude for this is that confinement survives in the large n and continuum limits. So, okay, how to understand this? Because the gravity solution does not predict confinement. So to understand this, I have to give some motivation again from the conventional ADS5 CFT4 correspondence. And as it is nicely explained in these papers, for high enough energies, I have only one saddle that contributes to the partition function. This is a big black hole in ADS. As I lower the energies, there is a transition where I have a small black hole localized on S5, which has negative specific heat. And then I have a Hagedorn transition, as Denjo explained. And then to even lower energies, I have a graviton gas, which is spread in ADS. So I can play the same game for the matrix model. And what we are proposing is something analogous. So we are proposing that in the large n limit and at small energies, we have the following sort of phase diagram. So for high enough energies, we still have a black D0-brane in 10 dimensions. Then as we lower the energy, there is again a phase transition, but this transition now, as I will explain in the next slide, it corresponds to a Gregory-Laflamme instability. So then I have an 11-dimensional Schwarzschild black hole wrapping, going around X11. Again, it has a negative specific heat. And as I lower even further the energies, I have a graviton gas, which now is in 11 dimensions. So this phase diagram gives me a transition from a 10-dimensional spacetime to M theory as I go to low energies. So the idea then is that there is a big overlap between phases in very small energies, which is given by this big gap between T1 and T2. So in the large n limit, there is a overlap between the two. And now I'm going to explain how to get this T2 and T1. So in a usual first order scenario, you have something like this, where the Polyakov loop and the temperature, they have this kind of behavior. And the idea now, the question is how to determine T1 and T2. So T2 corresponds to a Gregory-Laflamme transition, or equivalently a Gross-Witten-Wadia transition because the Polyakov line develops a gap, as Hiromasa explained. And the idea of Gregory-Laflamme is that when you have a black string which wraps the one circle, then there is a critical point when this black string collapses to a localized black hole. So this there's going to be a talk, I think, later about this transition by Paulo Figueras. But of course, there are many people who study this, and specifically for matrix model, it has been studied mainly by Kudo and Wiseman. Now, T1 responds to a maximum confinement or minimum deconfinement temperature because it is, again, suppose that I have a black hole, the Polyakov loop has to have an expectation value, so I am in the deconfined phase. So I ask the question, what is the minimum black hole that I can construct? And this motivates to use a Schwarzschild black hole in 11 dimensions with mass of to the order of the Planck. So if you do the calculation, you get a scaling of the energy, which is n to 1/3. So in the Lagrangian limit, the temperature, the difference between these two temperatures it becomes almost infinite. Good. So now I'm going to introduce another model, which is called BMN from Berenstein, Maldacena, and Nastase. And the difference with the model I presented before is that it adds massive terms it adds some mass on bosons and fermions, as well as a Myers term. And this Myers term gives some fuzzy sphere phenomena. And the idea is that the SO3 potential, so the bosonic potential in a SO3 subspace, it is of this form. So the trivial vacua are located here, and the fuzzy sphere vacua are located here. It also adds an explicit breaking of the symmetries from SO9 to SO3 times SO6. And even though the SU2 vacua are important and very interesting, today I'm not going to focus on this. So the question we can ask here is if the singlet constraint is important. And this question was asked by Maldacena-Milekhin, where they consider these BFSS and BMN models, and they asked whether or not the non-singlets play a role. So to motivate a little bit, the gauged partition function is given by this equation, and computing the equations of motion for the gauge field gives rise to this constraint, which is known as the Gauss constraint. On the other hand, in the ungauged version, you don't have a gauge field, so there is no gauge singlet constraint, and you have an extended Hilbert space which hosts these non-singlets. And Maldacena and Milekhin propose that the non-singlets, they are not important in low temperatures. Specifically, they say that they should be exponentially suppressed as you go to very low temperatures. So this idea was tested for BFSS a few years ago, and recently we tested it for the BMN model. And we find that indeed it seems to be promising. So you can test this using different observables. For example, here I saw the energy of the gates, so the difference of the energy between the ungauged and ungauged model. And you can see here the points follow an exponential decay trend. So I can do a fit about this, and the fit is exponentially suppressed. On the other hand, I also saw the perturbative results because the BMN model, it can be weakly coupled even in low energies. And the reason is this, because I can construct another effective parameter, an effective coupling, which will be lambda divided by mu cubed. So mu is the flux or the mass, and the result is that when you take the large mu limit, you can construct perturbation theories in 1/mu, but then your theory decouples in two different sectors. One sector is free, and it is the U1 sector, and the other sector is the interacting theory, which is SUN. So the low energy, the modes that contribute to the low energies are the ones that contain to the U1 theory, which is this blue equation here. And this is the result in the large mu limit and very low temperatures. At the same time, the fit is done for very low temperatures, but it is a conjecture for very small mu. And what you see here is that the conjecture by Maldacena-Milekhin, it approaches the perturbative U1 sector, but remember that this red line here is non-perturbative. So here, the powerfulness of the non-perturbative phenomena is revealed. Thank you. So one, I think, more interesting study is to try to understand, to compare the energies of the black D0-brane, so the energy that comes from the gravity, and the energy that we find in matrix models. So of course, there has been a lot of work in the deconfined studies in general for BFSS and BMN, and an incomplete list is over there. I apologize if some of you are not there. But the idea that I want to test now is this equation here. So the energy of this geometry is proposed to have a scaling of this form. And the only available analytic solutions or the analytic knowledge concerns the terms which are highlighted in blue. So the first term, which is the very low energy predicted by supergravity, and the 1/n² term, which was computed by curvature corrections. So for the BMN model, even though we don't have a known analytical known gravity dual, a first step was taken by Costa, Greenspan, Penedones, and Sandoz, where they constructed a deformation of this black D0-brane geometry. And the deformation was concerning only the supergravity term here. So they tested how the energy or the geometry will be deformed by changing the flux mu. And it is important to highlight that even in this case, the work which was done was numerical, because analytically we don't have a good control of the system. So David showed in his lecture some graph where the energy and temperature is compared from a paper by 2016, if I recall. And today I want to improve a little bit this picture. And what I want to do is I want to go to the large n limit, which this term here will vanish. And I want to focus only in the supergravity case, as it might become clear, because in very small temperatures, you have negligible alpha prime corrections. And what I get is the following. Again, this is some ongoing work, which I hope to be out the beginning or middle of next month. And here I'm showing the BFSS points, which was reported also in Georg's, in David's talk, highlighted here in purple. And the new points that we were able to construct were these red ones. So these red ones are large n and continue, but with finite mu, which is the mass. Here, actually, there are two lines. One is the black D0-brane by Izaki et al. And there is a blue one, which is studied here. So it is supergravity for finite mu deformation. But the difference is so small that it is almost negligible. And even though the BFSS points stop here, we were able to create 3 more points going towards the small temperature region, where these points start to converge with supergravity results. Again, so here in higher temperatures, I expect to have alpha prime corrections contributing. That's why I have this deviation from the supergravity. But the important point is what happens here in low temperatures. And this actually is a precision test. Specifically for the 0.3 point, we have a non-negligible amount of data that support this very nice. And there are some preliminary results for 0.25 and the finite end result for 0.24. Below this, instabilities start kicking in and we don't have a good control of the system. So this brings me to the synopsis of the talk and what do we learn from this. So we learn, first of all, that these specific matrix models are interesting test examples to study holography. I hope that I convinced you somehow that a confined and stable phase has been observed for the first time and what is the meaning of this confined phase. Of course, this is just a hint and many more studies have to follow to support or test this hypothesis. And for this, we have to better study the Schwarzschild black hole, the membrane, the 5-brane, and understand how these objects appear in the matrix models. So the idea of singlet constraint actually tells whether or not gauge symmetry is important to understand gauge gravity duality. And in low temperatures, precisely for the matrix model, it seems that it doesn't play a very important role. The last thing is that we have tested, we have made a precision test for holography for very small temperatures, building more and more trust for the idea of holography or gauge gravity duality, specifically again in these matrix models. But of course, more studies are important to understand what is precisely going on. Thank you.
Thanks, Stratos, for that wide-ranging talk. Are there questions? There are.
So usually when we have a theory with a gauge symmetry, one way to implement it is to forget about it and to introduce a penalty on the Gauss's law constraint, right? So in this case, what's going on? Is it being generated dynamically? That the penalty is kind of showing from the dynamics, and therefore that's why this must decouple?
So the way that the gauge symmetry or the non-gauge symmetry was implemented in this case was for the ungauged simulations, let's say, we fixed the Polyakov loop to be 1, to have a specific value. So it's not dynamical. And we leave the gauge sector to be dynamical. So the Polyakov loop fluctuates and with a Monte Carlo history. And we compared what is the difference between observables. One of those was the energy, but we also test observables like the Myers term or the sum of the trace x squared, and they all show an exponential decay. That's how we did it in this specific example. Now, there might be other more clever ways to do it that I'm not aware of. And of course, it is an interesting possibility.
Thank you.
Yeah, just to follow up on that, can you repeat what you did, how you did you fixed the gauge field So the Polyakov loop is 1. Is that what you said?
Yes.
Why didn't you just quench the gauge field? Why didn't you just turn it off
Why?
to have it ungauged?
Yes. So for the ungauged, so I don't have, so for the ungauged model, we fix the Polyakov loop to have a precise value. This is 1, and it doesn't change, it doesn't, so in a sense, it is turned off. It doesn't.
I don't think so.
Is this equivalent to setting all the gauge links to unit matrices?
Yes.
They just sort of pass through the calculation without any effect? Maybe we can think about
If you
that.
set all the gauge fields to unit matrices, that's one thing, but just setting the Polyakov loop to 1 is not the same thing.
No, it's not, but it's a consequence.
Yes.
Yeah.
Yes.
Okay.
So
But that wasn't the one I wanted to focus on. Was your unusual this unexpected transition?
yes.
Can you say a little bit more detail on the simulation? What
In confinement, deconfinement, you
in
mean?
the deconfined? Yes.
Yes. So I think the best thing is to focus here.
So what value of n did you test it at?
Yes. So this particular thing was for n equal 12, but what we observed was that as you go to lower temperatures, you get confined signal. So your simulation can be stabilized in the confinement phase.
But that can be lattice dependent.
Yes, but here we saw that in the continuum limit, you get that the energy goes to 0.
How did you get a continuum limit with n equals 10?
By simulating on n and taking different lattice points.
But you have an instability.
No, because when good. So we focused, we fine-tuned the simulations to remain in the confined phase. And this can be done by introducing, let me back off a little bit. What we observed was that in very low temperatures, there is a big hysteresis between confinement and deconfinement. So what we did was to introduce confined initial configurations to make the simulation flow in the confined phase. So when the simulation stays here, what we observed is that we don't have a runaway behavior. We don't have instabilities because the confinement is a band of eigenvalues that live happily together and nothing flows.
I mean, I checked this with some of our code, so I get instabilities there. So I'm just, we should talk about it.
Yes, I would be very happy.
That's very interesting.
Yes, yes, yes.
So how big was your lattice in the time direction?
Sorry?
There's the time, there's the temperature direction. How big was your lattice in the temperature direction?
The lattice here was 24, but
okay.
yes,
that
yes.
might be the question.
It is small. But,
The 72 though?
sorry? Yes, exactly. So
that's
here,
this.
so here, the previous one was 24, but the lattices we used was from 30 to 72. So this is, I mean, it's not really small, but the difficulty, of course, as you know, is that yes. So here there are signals so the simulation here is that if it would be in the deconfined phase, we would expect quickly to turn back on, like what's happening here. But here there is some 10,000s of Monte Carlo histories that it remains there.
That may not be long enough, though. I mean, I can show you my comparison.
Yes, of course, yes.
I thought I saw another question from Navdeep.
So yeah, just continue the same question. So do the order of taking limits affect any of the results? Large n, taking n tending to infinity and then continuum, or first taking continuum and then taking n?
So yes, first what we did first was to take the continuum limit and then the large n. But now we are improving the methods to have it a simultaneous large N and continuum extrapolation. So that's what we are studying now.
And you have combined the plots for energy and Polyakov loop.
Yes.
Do we have some intuition from the scalar squares? I mean, how should they behave in both the phases?
The trace x squared.
The trace x squared.
Yes, so actually it was here, but I removed it to make it a little bit cleaner, but it is stable and it remains stable, so it doesn't change when the Polyakov loop jumps. I can show you, of course.
So they are also following the same trend as energy and Polyakov.
Yes.
And I think that takes us to the end of this morning's session. So let's thank Stratos.